Okay, in this video we'll be looking at a method for finding the relative extrema of a particular function. Extrema is the plural for extremum, which refers to either a maximum or a minimum value. Let's look at the first example and we'll look at the graph so we can clarify what we're talking about. It says find the location and value of each relative extrema for the given functions. So I'm going to take my calculator, and I have the function already entered here, 2x to the third minus 3x squared minus 36x plus 14. Now I'm going to have to adjust the window so that we can see the function in the screen. So let me make an adjustment on this. Let's say minus 70 on the y. And 70. And then I just hit graph. And there you have the graph. Okay. So basically a maximum or a minimum, a relative maximum or a relative minimum value of a function is where the function reaches a high point. So it's kind of like a parabola. So we see the graph here. The graph is rising. It reaches a high point right there, and then it turns and goes back down. This point right here is the relative maximum of this particular function on this interval here. Now, if we continue, the graph continues to fall over here, reaches a low point, and then it turns back up. So anytime the graph changes direction like this, or it goes up and then down, or it goes down and then up, you expect to find a relative maximum or a relative minimum. Okay, so the relative extrema refers to these particular points, and you can have as many as you have loops in the graph. So I noted this last time in the last video where I was finding critical numbers. So notice that the tangent line, if I look at this particular point to the left here, the tangent line goes this way, which means positive slope, which means the derivative is positive to the left of this particular point. To the right, the line now, tangent line goes this way. That has a negative slope. Okay, so this point right here is called a critical point. The first component of that point is the critical number or critical value of the function, and the second component is the actual maximum. If I go to this one right here, this particular point here, the first component is the critical number, and the second component of that point is the minimum value or relative minimum. Okay, so basically then to solve the problem, we need to find the critical numbers, which is what I was doing in the last video. And again, as we saw in the last video, the critical numbers are found by simply finding the derivative of the function. So I find f prime of x. So we take the derivative term by term. It's a nice polynomial, so the first term has a derivative of 6x squared. Okay, so this is 6x squared minus, and the derivative of the second term is 6x, using your basic formulas for derivatives. The derivative of minus 36x is minus 36. And the derivative of 14, being a constant, is 0. Okay, so again, remember the critical numbers or critical values of a function are those numbers for which the derivative is 0 or for which the derivative is not defined. And they do have to be numbers in the domain of the function. Now, again, for polynomials, the domain is all real numbers, so we don't have to worry about undefined numbers or values that make the function undefined. So all we have to do now really is find the value that makes the value or values that make this derivative 0. So one way to do it is to factor it. So I'm going to factor out a 6 here. And that's going to leave me in the parentheses then with x squared minus x minus 6. And then basically it's like solving this quadratic equation. When is this equal to 0? So I'm just going to factor it. This factors into x minus 3. And x plus 2. So you can see from that the numbers that make the derivative 0 are 3 and negative 2. Okay, so the critical numbers are negative 2 and 3. Okay, so these would be the numbers that correspond to in the graph, to correspond to the points where the graph reaches a high or a low. Okay, so if you call the graph, first one, the first loop was opening down, so we had a maximum. The other one was opening up, so we had a minimum. So actually we have a relative maximum at negative 2 and a relative minimum at 3. But you have to justify that using the derivative. So remember what I mentioned on the graph and what I mentioned in the last video. One way to do it is what is called the first derivative test. So you simply check the sign of the derivative to the left of negative 2 and to the right of 2. So if it goes from plus to minus, the graph basically goes this way. If it goes from minus to plus, it's coming down, so we have a minimum. So in this case, I pick a number to the left of negative 2. Okay, so let's say negative 3. So I pick a negative 3. So let's go back over here to this factored form. I put a negative 3 right there. That would be a negative 6. I put a negative 3 here. That would be a negative 1. So because I have a negative here and a negative here, that's positive, times 6 will be positive. So basically to the left of negative 2, the derivative is positive. Now what happens to the right of negative 2? So let's pick a number to the right of negative 2. Let's say 0. Put a 0 there, put a 0 there. I get a negative 3 times a 2 times a 6. Okay, that's negative. So the derivative goes from plus to minus. So basically what this tells me is that the graph is going up, and then it reaches a high point at negative 2, and then it starts to turn down. So you can see that's a relative maximum. Now what happens at 3? Well, at 3, we pick a number less than 3, say 2, put a 2 there, put a 2 there where the x is over here. So it's 2 minus 3 is a negative, 2 and 2 is positive. So I have a negative times a positive, so basically it's going to be a negative. I already have it there. To the right of 3, pick a number larger than 3, say 4. So 4 minus 3 over here, and 4 and 2. I have positive, positive, and a positive 6. This gives me a positive. So this tells me then to the left of 3, the derivative is negative, so the graph is coming down this way. And then it reaches a low point at 3, and then it turns, the derivative is positive, so the graph is going up. So it looks, yeah, it's going down, and then it's going up, so it reaches a low. So we have a minimum, or relative minimum, at 3. So the instruction set, find the location and value of each relative extrema for the given function. Well, the location of the relative extrema, in this case a maximum and a minimum, are at negative 2 and 3. So one way we can write this is to simply say this. So I go ahead and evaluate the function at negative 2. Now you can use your calculator, or you can refer back to the graph and use the graph and your calculator to do this, but f of negative 2, in other words, the value of the function at negative 2, so if I put a negative 2 where the x is here on the function, I get 58. So this is then a relative maximum. So at -2, at x equal -2, the value of the function is 58. So 58 is called your relative maximum. Okay, do the same thing at 3. So evaluate the function at f of 3. And again, you can easily do this on your calculator by just using the table on your calculator, or just use the calculate menu and get it from there. But it's basically just plug it in 3 where the x is. So if I plug in at 3, I get a -67. Okay, the relative minimum then occurs at x equal 3, and the value is -67. So the relative minimum is -67. Okay. So the actual critical point, which I referred to in the last video, for this function is -2 and 58. -2 and 58 then would correspond to your relative maximum point, and the point 3 and -67 would refer to your relative minimum point. So again, that's 3 and -67. Okay, so let's clear this one. And let's go to the next one. Again, we have a nice polynomial. Everything's defined here. So to find the relative extrema, we simply take the derivative of this, and that again is going to be basic polynomial. So we'll have 4x to the third minus 3x squared. Again, a polynomial is defined for all numbers. So again, a critical number is a number in the domain of the function for which the derivative is 0 or undefined. So in this case, since everything is defined, this function is defined for all real numbers. The only thing we have to do then is find the numbers that make the derivative 0. So we factor out an x squared, and we're left with 4x minus 3. Okay, so you can see then that this derivative is going to be 0 whenever the x is 0. So I put a 0 here. 0 times anything is 0. So 0 would be a critical number. Okay, 0 is a critical number. So 0, critical number. And of course 4x minus 3, if you set that equal to 0 and solve, you get 3/4. So the critical numbers are 0 and 3/4. Now again, I want to point out to you that if a function has a relative extrema, that is either a maximum or a minimum, it's going to occur at the critical numbers. Okay, now I do want to make it clear that just because you have critical numbers doesn't mean that those numbers will lead to a relative extrema. Okay, it has to depend on the derivative. If the derivative changes sign at that particular value, then you do have either a minimum or a maximum depending on the sign change. But in this particular case, notice that if I pick a number less than 0, okay, to determine the sign of the derivative, so I'm going to pick, say, a -1. I put a -1 there. -1 squared is positive. -1 times 4 is -4 minus 3 is -7. So this is a negative times a positive. So to the left of 0, the derivative is negative. Now let's pick a number to the right of 0. Now because the next critical value here is 3/4, I want to stay less than 3/4 here. So I'm going to pick 1/2. So I'm going to pick 1/2. 1/2 squared is positive. 1/2 times 4 is 2, and 2 minus 3 is negative. So this product will be negative. So notice in this particular case that the sign goes from minus to minus. It doesn't change signs. So even though 0 is a critical number, it doesn't lead to a relative extrema because the sign does not change. In order to have an extrema, either a maximum or a minimum, it has to go either minus to plus or plus to minus. So in this case, it doesn't do that. Now let's write 3/4. Obviously to the left of 3/4 it's already negative. So to the right of 3/4 I'm going to pick 1. Put a 1 here where the x is. 1 squared is positive. 1 times 4 is 4, minus 3 is positive. So this product is positive. So in this case, at 0, it doesn't change sign, so there's no relative extrema at that particular value. At 3/4 it goes from negative to plus, so the derivative then changes sign. So negative derivative means the graph is falling, and then it reaches a low point at 3/4, and then it changes sign to positive, so it loops this way. So there is a relative minimum at 3/4. So then I'm just going to say f of 3/4 is equal to, and again that's just plugging in into the original function as 3/4 to the 4th power, 3/4 to the 3rd power, and then you subtract those, or use your calculator, or use the graph. Well, if you do the calculation either way, this gives me a negative 27 over 256. So f of 3/4 is equal to a negative 27 over 256. This is then your relative minimum. So again, at x equal 3/4, the graph reaches a low point, and the minimum value at that particular value of x is negative 27 over 256. Okay, so again, this particular function had two critical numbers, 0 and 3/4, but only one of them led to an extrema, in this case a relative minimum. Now obviously you can use this type of concept in some word problems that will be coming up where you're maximizing a function or minimizing a function. Could be a profit function, could be a revenue function, but we'll look at those types of problems later. So this concludes the video. So again, as always, please stay tuned for the next video. Any comments you have I appreciate, and please subscribe, and we'll see you in the next video.